Hi, in this video I'm looking at this problem here where we have a town of 8,000 people and 15 people have a new strain of the flu. The spread of that flu has been modeled using this differential equation here, dp dt equals 0.00014 p times m minus p, where time is in weeks and p is the number of people infected. And we want to develop an expression for the number of people infected over time, and then calculate the number of people infected after 3 and 10 weeks. Now this equation is a logistic equation where we have over time, we have a population, and our curve starts off at some initial population, exponentially increases, but then logarithmically asymptotes to a line, and this line is the value in our population is m, which is sort of our maximum possible population, which makes sense here because if we've only got 8,000 people in the town and we're just talking about the population of the town, we couldn't do more than 8,000 people. So we'd quickly infect a lot of people, but then it would slow down because it's a bit harder to find people that are not infected, to a point where we approach and generally not quite get to the full population being infected. So that means that if we're going to start looking at A, our value M is our maximum population here, 8,000. So we can rewrite our equation dp dt equals 0.00014 times P times 8,000 minus P. And so now we've got only P's and T's in here. We can look at trying to solve this differential equation and get an expression for P. So let's do that. The first thing I'm going to do is get everything that involves a P onto the left-hand side. So I'm going to take this bit here, P times 8,000 minus P, and I'm going to divide both sides by it. And everything that involves a T onto the right-hand side. So I'm going to take this divided by dt and multiply both sides by it. So that means that we're going to have, on our left-hand side, we're going to have dp over p times 8,000 minus p. And on our right-hand side, we're going to have 0.00014 times dt. And then our next step is, now that I've isolated all my variables, I've got to integrate both of these sides. So I'm going to take the integral of both of these sides. Now to find the integral of 1 over p 8,000 minus p dp, I'm going to have a look at dealing with this fraction. So I'm going to come over to the side over here, and we're going to have a look at this 1 over p times 8,000 minus p as a partial fraction. So that means that I've got a over p plus b over 8,000 minus p is going to equal 1 over p 8,000 minus p. And we've just got to figure out what a and b are. So if I add these two fractions together, I'm going to have a outside of 8,000 minus p plus b times p, so multiply up, and then multiply the denominators together. And so that's still equaling p outside of 1 minus p. So these two fractions are equivalent. They're the same, so that means that I can ignore the denominators because they match up and just focus on the numerators. So 1 equals a outside of 8,000 minus p plus bp. And so let's expand this bracket here. So I've got 1 equals 8,000 a minus a times p plus b times p. And now I'm just going to look at the bits that have p's and don't have p's. So this bit doesn't have any p's, so I'm just going to leave it as 8,000 a. These two both have p's, so I'm going to factorize out those p's, and that means that I'm going to be left with positive b negative a, so b take a, and that'll equals 1. So now we want to equate the stuff on the left and right that both contain p's and don't contain p's. So here I've got these two do not contain p's, so that means that 8,000a equals 1. So that means that if I divide both sides by 8,000, I've got 1 over 8,000. Oops, one too many zeros. And if I look at the bits that have a p, I've got this bit and I've got 0p basically. So that means that p outside of b minus a is going to be 0. So I can divide both sides by p and just be left with b minus a equals 0, because 0 divided by anything is 0. And so that means that b is going to be equal to a, because if I add both sides to a, I'm going to have 0 plus a is a. So that means that b is also 1 over 8,000. So that means that if I go back to our initial fraction we started off with, 1 over p outside of 8,000 minus p is going to equal a over p. Well, a is 1 over 8,000. So I've got 1 over 8,000 over p plus b over 8,000 minus p. So b is 1 over 8,000 over 8,000 minus p. And so I can sort this out a little bit tidier by factorizing out those 1 over 8,000s and be left with 1 over p plus 1 over 8,000 minus p. So I can now put that back up into my integral that we had up here. So now this is going to become the integral, let's go slightly neater integral, the integral of 1 over 8,000 multiplied by 1 over p plus 1 over 8,000 minus p. And we still have dp. And that's going to equal the integral of 0.00014 with respect to t. So now looking at doing these integrals, on the left, I'm going to leave the 1 over 8,000 as a constant out the front, multiplied by, now the integral of 1 over p is the natural log of p. The integral of 1 over 8,000 minus p is going to be the natural log of 8,000 minus p, but I've got to divide by the derivative of the 8,000 minus p, and the derivative of 8,000 minus p is just going to be -1. So I've got to divide by -1, so instead I'm going to just change the plus to a minus, and so that leaves us with our left integral. And our right, 0.00014 dt is just going to be 0.00014 times time, but of course we've got to have a constant of integration. So now that I've done my integrals, I need to isolate p, because we want an expression for the number of people infected, and p is that number. So we want p equals an equation in terms of time. So the first thing we're going to do is multiply everything by this by 8,000 to cancel out this over 8,000. So that's going to leave us on the left with just ln of p minus the natural log of 8,000 minus p. On the right, 0.00014 times 8,000 gives us 1.12, and we still have t. And our constant is going to be multiplied by 8,000, but a constant times a constant is just a constant, so I'm going to leave it as plus c. So now I've got to deal with these two natural logs. Now I've got now there's a log law that says that if we've got the subtraction of two logs, then you can have the log of the derivative of the inside. So we've got p over 8,000 minus p. is going to equal 1.12t plus c. Now we can undo our natural log, so I'm going to raise both sides to the power of e, so that's going to leave us with p over 8,000 minus p equaling e to the 1.12t plus c. And so we can deal with that plus c there by bringing out the front as a constant a. So we can have a e to the 1.12t, where a is going to be e to the c, because we can separate out that e to the 1.12 plus c as e to the c times e to the 1.12t, and so the e to c just becomes a constant a, because a constant to a constant is just a constant. So we're almost there. I've just now got to get 1p and I've got 2p's. So what I'm going to do is I'm going to multiply both sides by the 8,000 minus p. I know it seems like we're going a little bit backwards, but it'll work out in the end for us. So we've got p equals 8,000 minus p multiplied by ae to the 1.12t. And now I'm going to expand these brackets. So we've got p equals 8,000 times ae to the 1.12t minus p times ae to the 1.12t. And so now I'm going to add this p ae to the 1.12t to both sides. So over here we're going to have p plus p ae to the 1.12t equaling 8,000 ae to the 1.12t. And so I can now factorize out a p. So we're going to have p outside of 1, because there's only one p here, plus the ae to the 1.12t equals 8,000 ae to the 1.12t. And so now I can divide everything by this 1 plus ae to the 1.12t. So we can have p equals 8,000 ae to the 1.12t divide by 1 plus ae to the 1.12t. Now we could leave it like that, but there's one last step that we can do just to make it so that we only have one t term here. And that's I can multiply by e to the negative 1.12t and over e to the negative 1.12t. So I'm multiplying by 1, so it doesn't change the equation, but it means that on top, e to the positive 1.12t times e to the negative 1.12t cancels out and just becomes 1. So on the top we get left with 8,000 a. On the bottom we've got 1 times the e to the negative 1.12t, so that's just going to be e to the negative 1.12t. But again, on the second term, the e to the 1.12t times e to the negative 1.2t is going to cancel out to become 1, so we just get left with plus a. And so that's our expression, but we've got to clear out this a. We need to deal with this constant a. So if we go back up to our question, we were told that at the beginning, 15 people have that new strain of the flu. So that means that if I come over here, we can work out a, because at time equals 0, our population p is 15 people. So if I put that into our equation, I've got 15 people equals 8,000 a over e to the negative 1.12 times by 0 plus a. And so e to the 0 is just 1. So we've got 15 equals 8,000 a over 1 plus a. So now I just need to isolate a. So I'm going to multiply the 15, well, both sides by the 1 plus a. So we're going to have 15 multiplied by 1 plus a is going to equal 8,000 a. So then we will expand this bracket. So we've got 15 times 1 is 15, plus 15 times a is going to be 15a, equaling 8,000 a. We can minus off 15a from both sides, so we get 15 equals 8,000 a minus 15a. And so we're going to have 15 equals 7,985 times a. And then we can just divide both sides by 7,985. And so that's going to leave us with 15 over 7,985, which means that a is going to be the fraction 3 over 1595. So now we can put this up into our rule over here. And so we're going to have p equals 8,000 times a, which is times by 3 over 1595, over e to the negative 1.12t, plus a, which is 3 over 1595. To tidy this up just a little bit, I'm going to multiply top and bottom by 1595. So that way we can get rid of this over 1595 in both times. So the 1595 is going to cancel off the top. And so we're just going to be left with 8,000 times 3, which is 24,000. Over, well, 1595's got to times both of these terms. So the 1595 will multiply onto the e to the negative 1.12t. But over here, when we multiply these two, are going to cancel out. So we're just going to be left with plus 3. And that, finally, is the result for part A. This is our expression that for number of weeks' time after the infection started, our population is given by 24,000 over 1595 e to the negative 1.12t plus 3. But we're not done yet. We've got to finally answer part B. Calculate the number of people infected after 3 and 10 weeks. Thankfully, that's nice and easy. So at t equals 3 weeks, we've got our population rule, which I will write out again up here. P equals 24,000 over 1595 e to the negative 1.12t plus 3. So if we substitute into our rule, t equals 3 weeks, so we got 24,000 divided by 1595 e to the negative 1.12 multiplied by 3 plus 3. And if we work that out, that means that we have 410.94. So therefore, after 3 weeks, 411 people are infected, approximately. And if we do the same at t equals 10 weeks, that means we're going to have p equals 24,000 over 1,595 e to the negative 1.12 multiplied by 10 plus 3, and working that out gives us 7,942.23. So therefore, after 10 weeks approximately 7,943 people are infected. And that's it, we're done. So if we have a problem where there's some sort of cap on our exponential increase, then we actually have a logistic function which is modeled using this style of differential equation. So we can work out what all of our equation is by integrating and doing a fair amount of algebra, and we get to our end. And then of course we can just use that nice and easily to sort out what would happen in future times.